Andrey Trepalin, and the rationality of cubic surfaces over subfields.
Rationality of cubic surface. Okay, we start from the beginning. So, beginning is definitions. Right x is rational over k. If bi-rational equivalent to projective space of the corresponding dimension. It's stably k-rational. If there exists some numbers and such that the product of x by Pn is rational, equals to Pn cubic, and x is k unirational. If there is a dominant 9 in the map, from Pn to x for certain n. But one can define this condition and say that it is equal to the condition that there is a finite bi-rational morphism from Pd to x. In this case, we call the degree of this morphism of this map of P is degree of the irrationality. Yes. We have the following three implications. An irrational variety is obviously stably irrational, since one can put n big equals to d and n little to 0. And any stably irrational surface is obviously k-irrational, since one can consider projection of Pn onto the first factor, to x. So stably k-rational variety are k-irrational. The main question of today's talk is when we can converse these implications. So when stably k-rational varieties are k-rational and when k-irrational varieties are stably k-rational. What is known? The best known results are only for small dimensions. For if d equals 1, then by Neuron's theorem I'll have that any k-irrational curve is k-rational. And the conditions on the field K are trivial. K is arbitrary field in this case. For dimension 2, one have corollary from the external theorem. So we have the same result, but with some conditions on the field K. So any k-irrational surface is k-rational, but in this case, the field K should be algebraic closed, and characteristic of K should be equal to 0. For dimension 3 or greater, even for fields such that they are algebraic closed and characteristic 0, the converse implications are false. So there are some examples. Which was constructed that k-generational then imply stable k-rationality. Exams were constructed by Martin Mumford.
You mean doesn't apply? You mean doesn't apply?
Yes, it doesn't. Thank you. And other examples by Trepalin. What John Gordon. Well, it's about this implication. And the first implication that stable k-rational three-dimensional variety can be not k-rational. Was constructed by Bovil for the Trepalin. Samsung and Swim to die.
Yeah, but the standard Clemens examples with the intermediate Jacobian, don't they work? Because, I mean, you...
I think in these examples they use techniques of
To show stable rationality.
Yes.
Yeah, but
It's very non-trivial.
if you multiply this guy, the intermediate Jacobian doesn't change it.
No, it's not unidirectionality.
Yes, it's not irrational, it's
It's very, very
irrational.
stable rationality.
Ah, actually,
That's
okay,
that's
sorry,
irrational.
sorry, yes.
Oh, it's different word.
Well, so we see that even for this simple case where we have algebraic closed field characteristic 0, for dimension 3 or greater, everything fails. There are no implication in the back direction. But we missed one case. Case d equals to 2, but k is arbitrary. What is in this case? What do we know about rationality, irrations, and static correction? Well, first I want to remark that this example of static irrational variety of dimension 3 that is not k-rational is based on the case of dimension 2. Actually, one can consider static k-rational, not k-rational surface. I will write down this surface. So, and consider it over a functional field. So, this example, the dimension 3 case, is made by methods of dimension 2. So, what are these methods? Well, let's start think about surfaces over non-closed fields. If characteristic of the field is equal to 0, then any k-unirational surface is geometrically rational. That means that over algebraic closure of the field, minimal over algebraic closure. So, this trivial effect, since it immediately implies products to no criterion, we see just for algebraic closed fields, k-rational surface is k-rational, so just we replace k by k bar and have this result. Well, for these surfaces on characteristic 0 at least, on smooth case, one can apply minimal model proper and can obtain the following result. I think this theorem was proved by Miskowski, but the more general version are used in the paper of mine. Well, that has been geometrically rational surface. Over the field K, K arbitrary field. Then X is birationally equivalent to a surface X such that one of the following possibilities holds. The first is either X is a dependent surface that means that its canonical class is ample with invariant Picard number equals to 1.
Invariant, just because of.
Just Picard number invariant respective to the action of Galois on Picard lattice. Or the surface X admits a structure of conic bundle over curve, smooth curve G, genus 1, and Picard number equals to 2.
Genus 0.
Genus 0, yes. So all closure is just yes. 2. Yes, yes, this is 2. This x are minimal surfaces. That means that remark. The obtained types of surfaces.
Is it rho or p? What is this rho or p? What is it?
Rho?
Yeah.
It's a common.
Common.
Yes. It's just dimension of yes, right. It's less. Yes, types of surfaces are minimal. That means that any birational morphism from X to Y, where Y is smooth, is trivial. Is a morphism. Well, what does this mean? That for studying standard rationality,
So in the case 2, for example, it could be, for example, a root surface.
With the root surface, but then I-
it's not minimal.
but then I
It
can
satisfies your property, but it's not minimal in this.
I don't say that any surface with this property is minimal, but if for any surface S, I can obtain a surface X birational equivalent to S such that it is minimal. Yes? So if I obtain non-minimum conic bundle with required number 2, then I can go down some curves and get the minimal surface.
But in the first case, it is just after you pass to the algebraic closure, it will be P2, right? Or
So
not?
for algebraic closed field, yes, it's just P2. And the second case for algebraic closed fields is just Fn, Hilsebrook surface. So it can be P1 cross P1 or it can be some other Hilsebrook surface.
One comment. This theorem actually is Koskinen assumes that your field is perfect originally.
I think that in one version I don't found this restriction. So I'm not sure. I'm not sure. Maybe it's true, but
This proof is a little bit Mori proof is more.
so in
more general.
in Koskinen original paper, there is assumption that X is over perfect. But in Mann's paper and with subsequent 89th here, there is this assumption. Maybe it's necessary, but I am just writing what I read. Well, what's about our question? So, it means this theorem that to study cyclic-irrationality of surfaces and K-duration, we can consider minimal surfaces as any or geometrically irrational, at least in characteristic 0. Since in characteristic greater than 0, there can be some problems. There are these irrational surfaces which are not geometrically rational. And so we can consider minimal surfaces of the following two families: conic bundles and the bed surfaces. Well, what about our problems? First, K-rationality. There is this rationality criterion, which says the following: if K is perfect and X is minimal geometrically irrational surface, then there is equivalence. X is K-rational if and only if the following two conditions holds. The first one is that there is at least K point on X, which is obviously conditioned. And the second condition is that Kx squared is no less than 5. So the best surface of degree 5 or greater or algebraic closed level over arbitrary field minimal are rational over K, and of degree 4 and less, they aren't irrational if they are minimal.
So this perfect assumption is not calculus. The assumption for being perfect for the field is not calculus. No concrete examples if the field is not.
I don't know, so well, it's a result about K-rationality. What about K-generationality? There is a well-known theorem. I do not know who is originally the author, maybe Sweden to die, but everybody refers to the Mann book on cubic forms. So, Mann said us that minimal the better surfaces of degree 4, 3, and 2, such that there is a point defined over K, or even for the better surface of degree 2, this condition should be replaced by condition that K is dense. Well, these surfaces are always K-generational. And the degree of K-generationality is and 24 respectively. What does it mean?
At most.
What?
At most.
At most, yes. But if you can say that there is a map of degree 6 for any cubic surface that eliminates from map of P2 to any surface of degree 6. Well, what about this? So what does this theorem show? It shows that of algebraic non-closed field K, the distance between K rationality and K irrationality is very great. So, first, K rational surfaces, they are not the same as K irrational. Yes, since one can consider any minimal dependent surface of degrees 4, 3, and 2. There are lots of examples of these surfaces. And it's very easy to construct these surfaces. And the implication from K irrationality to K irrationality is false, and it's a very big distance. But between these two notions, K rationality and K irrationality, there is a condition of stable K irrationality. And one can ask about implications from stable irrationality to K rationality, and from K irrationality to stable K rationality. So, aim of our talk today is said that condition that a surface is stable K rational is very closely connected to condition that K rational. So there are very small number of examples of stable K rational surfaces which are not K rationality.
So what is one example?
I wrote down it soon. Just two remarks about unirationality, and then I started.
What is the degree of unirationality?
Of what?
Of unirationality. What is the degree?
Degree? It's a degree of finite map from projective space to this surface. So, if you have the surface degree of 4,
Is that near minimal degree or?
usually it's minimal, so we can say that at most, if to be precise. So, of course, there are some cubic surfaces with a degree of generation, 2 or 3, something like this. Well, about K-rationality, 2 remarks last. So we see that the best surfaces of degree 4, 3, and 2 are always K-rational, but there are 2 open questions, which are a big problem of 2-dimensional geometry of geometrically rational varieties. The first is are the best surfaces of degree 1 degree. So degree 1 is K-rational, K-unirational. So nobody answer for this question for arbitrary case of the best surface of degree 1, in particular with Picard number equals to 1. And the second question is the same questions about conic bundles. Unirationality of conic bundles over algebraically non-closed fields. So, for example, for the field of real number, Piskovsky showed that any surface admitting structure of conic bundle over rational curve is irrational of degree 2, but in general case nobody knows the answer. Well, this is about K-irrationality, and now I start talking about stable K-irrationality in dimension 2. So, what's the example? I mentioned this example when I consider the case of dimensional 3 or greater. The example of bovine, polyethylene, or sunsilk and swing to diamond. And that's the following. We consider a conic bundle with 4 degenerate fibers.
Geometrically, right?
Yeah, geometrical fibers. Such that components of these fibers are defined over extension of degree 6 with the Galar group S3, symmetrical group of 3 layers. And this group acts in the following way. First, there is rotation element of order 3, which just preserves the both components of one singular fiber and cyclically permutes the other 3 singular fibers. The second generator of this group is an element of order 2. This element changes to singular fibers and also switches all components of all singular fibers. So it acts like what I draw. Well, this is example of geometrically rational surface, admitted structure of conic bundle, minimal conic bundles, which is stably k-rational, but not k-rational. Since it's minimal, the square of k is equal to 4 in this case. By Stolz's rationality criterion, we have that x is not k-rational, and one can show that it is stably k-rational. Actually, it seems that this example is the only known. So there are some possibilities of other surfaces for which this surface can be stably k-rational, but it isn't proved. For this case, this example, it is proved that it's stably k-rational. What's the idea of proving of stably non-k-rationality? The idea is the following.
So, can you repeat which one is stably k-rational, which one is not?
This is stably k-rational. This is one example. These 2 generators of the group S3.
Okay.
Yes, this is a rotation element of order 3, and this is element of order 2.
Sorry.
So you see that it's minimal since there is an element which switches components of any singular fibers, and also in this example,
So this is
stably k-rational but not k-rational. Yes.
So I mean, non-directionality falls from Miskowski, and then they just need to prove that it's stably k-rational.
Yes, yes.
And that's basically 90% of the work is proving explicitly stable rationality
And how it is done?
in a very tough way. So well, basically you have to multiply it by some PM. So instead of this, they take some universal torsor with respect to some torus, which is like the Néron-Severi torus, but well, they can make it slightly smaller, but on the level of idea, it's a Néron-Severi torus. So it's at the very beginning it's large, but actually it can be made of dimension 3. Then I say that this universal torsor is actually locally trivial, and then it appears that it can be given by explicit equations with some quadratic spaces, like with section of two quadrics, and then they prove that this is a section of two quadrics rational. So it's a sequence of coincidences.
It's how to prove that this thing is not
No, it's stable rational.
That is stable rational.
So some very explicit construction, and that's why that's the only example, because
It's quite difficult to repeat this construction even for the known cases, which can be stable rational. Well, But what's the step to prove how to show that a surface is not stably irrational? There is a necessary condition of stably rationality. K rationality is the following: if X is stably irrational, then for any finite separable extension of K, extension K prime or K. The following groups, the following group vanishes. H1, then the modular group of K prime into colors or gray closures. So if at least one of these groups is not trivial, then X is not stably K-rational. So to prove that X is not stably K-rational, one should find an extension such that this group is not trivial. Well, what is the method and how to find this group? We see that absolutely Galois groups, it acts on our surface over algebraic closure, and then particularly it maps to the group G of automorphisms of the Picard lattice. But not all automorphisms. This automorphism should obviously preserve the anticanonical class or canonical class just and intersection form. Well, let us consider the basis of K's orthogonal in the Picard lattice. What do we have? We have that, well, first about conic bundles. It's known that if the L-tau field is algebraically closed, that one can blow down a number of components of singular files and get a Hertzbruch surface. Therefore, the Picard group of conic bundles is generated by class of section any, class of fiber, and classes of exceptional divisors of the globe over the back close roof of field of X. For X conic bundle. What can we do with this set of generator? We can consider the space take X bar cancelled by, for example, Q or any other line of space, intersected with KX orthogonal and intersected to F orthogonal. Yes? Which looks like difficult, but you see that any G acting on our surface X, it preserves canonical class. If X is conic bundle, it also preserves the class of fiber, and it acts on this construction. What is the basis for this space? The basis is following. One possible basis. F minus E1 minus E2, E minus E2, E2 minus E3, etc. E n minus 1 minus En. Why this basis is good? Since the square of any element of this basis is minus 2, and they, the generators, have the following graph of intersections. So two vertices connected by an edge. They have intersection 1, and two vertices which are not connected by the edge don't have intersections. So what do we see on this picture?
So we have E1 minus 2 twice.
It's no. I write down more. Here is F minus E1 minus
Yes.
E2. So you see, if square is 0, a square of any element of this set of generators, and E1 square and E2 square are minus 2. Well, I think I should leak it and write it. Well, so in this case we have that the group G is subgroup of the Y group Dn, of type Dn. This is Dn root system. And this is G maps to the automorphism group with Dn. What in the cases of the best surfaces? As in previous case, we can write down the set of generators of the group Picard X bar. It will be L, which comes from the class of line from P2, and some number of exceptional devices. Its basis Picard group, and the group, the Galois group and the group acting on X, also should act on the following space. Or we can Picard group by Q and intersect it with the orthogonal of Kx. Now we have this space, and we could write down the system of generators. Yes, and assume that n is no less than 3. Yes. What do we have? We have E1 minus E2, E2 minus E3. Here we have L minus E1 minus E2 minus E3. And then, for n greater than 3, E3 minus E4, E4 minus E5, until En minus 1 minus En. We have squares of each of these elements in the basis. Square is minus 2, and intersection looks like the following. So I start drawing. This is for 3. W is root system. So the best surface of degree 1 is law of 8 point, and for n equals 3, the root system is A1 times A2. For n equals 4, it's A4, then D5, then E6, E7, and E8 last. Well, now we have that for the best surface of degree greater than 1, we have that G maps to the subgroup of the one group E and En just, yes. Well, we can define E5 as D5, E4 as F4, and E3 as F1. Well, what's about the method? Why do we need this while group? Well, the group G, which is the image of the Galois group in the L group, is called the splitting group of our surface X. And finding subgroups of G, of splitting group, corresponds to find extension of our field K. So we can reformulate these conditions that we should what? To check condition which is written on this page. One can consider all finite subgroups of G.
Which condition?
This is a condition of stable rationality. So the condition that for any finite extension we have the cogomology are greater. Yes, these cogomology, they are the same for the extensions which have the same image in G, for example, yes? And so also we should just consider all finite subgroups of G in the well group and check that condition is true for this. And find H1 for the corresponding extension. Well, this method, so I think in all proofs of stable non-K rationality, they also use this method, or it's for this equivalent condition of this method. Well, now we can think about the better surfaces. So what do we have? If the better surface is minimal and has degree 5 or greater, then by Exposed rationality criterion, it is irrational. Actually, one could prove it for any field, even if not perfect. The next case is degree of the best surface is equal to 4. And there is a result of Kunyavsky, Skorobogatov, and Swassman. It's a result from 1989. Yeah? Kunyavsky, Skorobogatov, and Swassman. Fx is minimal, not only minimal, Fx is the best surface of degree 4, and the Picard angle is equal to 1, and also we assume that this k is non-zero. Then x can be stably irrational only if the group G splitting group is isomorphic to one of the following groups acting on the Picard group in a certain way. These groups are C2 times S3. By C2 I denote the cyclic group of order 2, and so CP is cyclic group of order 3. C3 semi-direct product onto C4 group of order 12, or semi-direct product of C3 and the equivalent group of order 8. Well, only three possibilities for Lubetza of degree 3.
But can be means just that the abstraction vanishes. So you
Yes, yes.
No,
It means that only for these three groups, X is minimal and all homology groups vanishes.
But do you mean x of k is not empty or?
X is not empty. Yes. Something I miss this things. This is known result, known odd result. One more modern result. It's about geometric situation, not a number theory construction. It is not very new result. It's well, maybe 3 or yes, I go 4. It's result of Yuri Prokhorov. You can remember when it was proved. For algebraically closed field, a group G is called stably linearizable, yes. If there exists stably conjugate to a subgroup of projection space. And here G is group of automorphism X. Yes. Conjugate to a linear action on P. What does result of Yuri Nadevshev say? The theorem that if X is G minimal and G minimal, that surface of degree 4 or less, then G is stably k-rational, looks stably linearizable. Well, G minimal, not G minimal, but where the number is 1. Here I should write. It's not true for the best surface structure of collimators. Stably linearizable. Only if the test surface has degree 4 and G is the group root here of order 12. C3 times R times C4. It's analog of this result in geometric case. So analog of stable k-rationality is stable linearizability. And we see that from this group, only one group can be realized as a group of automorphism, the best of degree 4. And moreover, there are not any group of automorphisms that can be realizable as the group of automorphisms, the best of degree 3, 2, and 1, for which this group is stably linearizable. But we now see that it may be not true in more general situation, in situation of number theory.
and the additional abstraction is the fixed points for the subgroups.
Additional, yes, something like this.
So that allows to get rid of the two other.
Oh,
That allows to get rid of two other candidates.
I think this group just don't act on the best of the form. Maybe, yes. So any group can be realized as a Galois group acting on the best, any subgroup of the Lie group can be realized as a Galois group acting on the best surface. But not any, of course, not any geometric groups, for example. Just involution, which permutes two classes of exceptional devices, can be realized for n greater than 4. Yes. This result of, maybe it's quite recent, but not quite. But last year, event was last year a peer result of polyethylene, which awakened interest to studying of irrationality. The result is the following. If K is quasi-finite field, quasi-finite, it means that any finite extension of K has cyclic Galois group. For example, finite fields are quasi-finite, and for example, the field of real numbers is quasi-finite too. Well, so if K is quasi-finite, then any geometrical rational surface and the geometric rational surface is K-rational if and only if it is K stable K-rational. So for the quasi-finite field we have implication in both directions. And stable K-rational surface is K-rational. What does it mean about quasi-finite fields? So fields quasi-finite, that means just that the group G is cyclic. Yes, the group G is cyclic, therefore these cases don't appear and all other cases too. So it's simply a situation, but we have a good corollary on this result, which I write for now. So this is the case of quasi-finite fields. But after this, interested to static irrationality awakened, and at something like 19th of February appeared not paper but text on a page of Chinky. So this text is yes, I just remember.
Do you need break?
I need break, but not now. I need to.
Mini break.
I just write the result of Chinky again, and this result which I want to prove today. And so then we'll have a break. Chinky and Kaichi, or something like this, young. Let K be arbitrary field, X minimal at best surface, minimal in the sense that the prime number is 1. Then the surface of the gradient. If D is equals to 1 or 3, then X is not static irrational. and if d equals to 2, then x can be stably k-rational only for the following four groups. It's the hydral group of order 14, semi-direct product of C7 and C6, the hydral group of order 13, and semi-direct product of groups of order 15 and 4, such that an element of order 4 neutrally actions by conjugation on elements of order 3 and order 5 more. So this is result. Also they proved some results, full results, about conic bonds with at most 7 singular fibers. So they consider all minimal surfaces with kx squared 1 or greater.
What kind of results for?
There are many cases. Yes, there are many cases, and it's quite natural. So what was idea of the proof? The result.
A little question. Can G also be trivial?
The group G?
Yes, I mean.
Of course.
if you are
G can be trivial, but if G is trivial, then all lines on either side is defined over K, and one can blow down a number of lines and get P2. Yes, in this case, G X is a K-rational, obviously. So we should have condition that X is minimal, so G should be not trivial.
So I mean, why don't you include trivial G in this list?
Since in this case, X
Picard number is
Picard number is not one.
Ah, okay.
So
the same as here, right?
yeah, the same as here, I write down. Picard number is 1. And what idea of their proof? They consider all finite subgroups in one group A8. For all these finite subgroups, they found, except the following 1, 2, 3, 4, 5, 6, 7. For those 7, they find subgroups such that corresponding cohomology doesn't vanishes. So they use huge computation using magma system, and they get a result. I get the same result without computational methods, and so I present some ideas after a little break.
10 minutes break.
The method of proving of this theorem was direct computation using magma. And our method of proving the same result is blind minimal model problem. Let's start. What's the idea? We have the result of polyethylene that says that if G is cyclic, X is minimal, then we have that X should be not standing iteration. How we can reformulate this fact in terms of G run minimal model problem? If in the group G there is an element G such that G equivalent minimum model program ends at surface Y such that ky square is no greater than 4. Since this is 5 or greater, then this short surface should be rational for the corresponding field extension, and in this case, cohomologies are trivial. Such that ky squared is no less than 4. Then X is not static rational. how to prove it. Consider an extension of fields, that is the group generated by G corresponds to this extension.
It's a probably not of Chinka, but of Trepalin.
Yes, or I have a place here to write down this chloride. Yes. Even I mentioned that there will be chloride. So we can consider an extension and go to cyclic group G. If this, for this cyclic group G, the minimum model has canonical class, square of canonical class 4 or less, we are in the situation of theorem of Collier-Thelen. And we know that for this situation, there exists a number n such that
Sorry, when we are in the situation of Collier-Thelen?
when we pass to the extension of field K, for which the group, the corresponding subgroup in the group G, is cyclic group generated by G.
But I had an impression that you
Frankly
said
speaking, you need maybe more general form of this, right? Because your group is not the whole group. Your group is.
It's not the law extension, yes, but it's, I can do this.
But so you get fields is not quite fine, right?
Yes, but
You need maybe.
it's not a problem. The method was that for finding group G, one could find such n that G or G.
Слушай, ну ты сказал, что это как-то связано с тем, что k в квадрате меньше либо равен 4, вот я не понимаю.
А здесь ситуация, что значит это квазиконечное поле, да? Я вот в таком виде записал.
Да.
Вот. Но реально он записывается в том виде, что как бы, если у нас конец квадрата больше 5, то она рациональная, значит фактически стабильно рациональная. А если конец квадрата меньше или равно 4, то оно не к-рациональное, а значит нестабильно к-рациональное.
Хорошо.
То есть вот, тут формулировка довольно дурацкая.
То, что было известно до того, что
Да,
это k меньше 4,
да.
значит она не...
Я прям знал, что...
Ну, просто мне не нравится этот вопрос.
So, G or G in S power has non-trivial H1 in this case. Well, so what can we do? In this situation, we check all subgroups of G, of the value of G. But we want to check only cyclic subgroup of G. So we write down the following definition.
So still it means that there is some computation needed, but smaller than.
Of course, but they all are done. They all are done. I cannot compute the chronology groups by myself. I use the known results. Now I know that I have G such that the minimal model program with G leads to the surface of degree 4 or less. Then G is better element. I don't need to compute everything. Everything was computed before. That's the idea, not to compute. So, well, I write down the following definition. So, we say that the group G for the group G, there is a cyclic construction if there is an element G in G such that G equivalent MMP and set a surface y with ky squared equals to 4 or less, so just to this condition. It's like a construction, this abstraction to be state declaration. Well, and also we will say for such elements for which this condition holds, we'll say that G is bad elements for simplicity. Other elements are good. What about good and bad elements? The conjugacy class of elements in the one group where W is 6, 7, and 8 were found by Frey in 50s, and more better method by Carter and 72, yeah, 1972. And also for all these conjugacy classes of cyclic subgroup of the Y group, WEN, for all these cyclic subgroups, the corresponding cohomology groups were calculated by Urabe. There are well known for somebody Urabe tables where there is a column where all these cohomology groups are written. For example, there is such a column in mine tables in his book on cubic surfaces, but only for conjugacy class and WE6. And for WE7 and WE8, these cohomology invariants are calculated in Urabe tables. So Kuryatilian used these computations to prove this result for cyclic group G, and I just reformulate this result in terms that it's I want to consider elements in terms of minimal model problems, not computation of H1.
This question, this proof of this theorem is also case by case.
Of this?
Yes.
It's also case by case, but it's very simple. It's really simple.
Okay. Okay. So he used
So maybe
classification
there
of-
is some untrivial for common bundle case, but for the cases of the patch surfaces, it's quite simple. You just found elements for which invariant number is 1, and then you look on their power and found from this power 1 for which H1 is not 0. Yes? For example, there are 2 types of elements in WE6, 2, such that the cohomology groups for these elements are trivial, but for the powers of these elements are not trivial. Yes, so it's case by case, but it's very simple for quasi-finite fields, so there is no problems. Well, we want to just consider cyclic subgroups, just consider the G equivalent MNP, and found possibilities for surfaces without cyclic abstractions. One remark that this cyclic abstraction is not is more less powerful condition that one would consider all subgroups of G, since there is example of action in cyclonic bundle with 4 degenerate fibers, and the group is C2 squared, such that action is the following. It's the first element, so both elements no, it's not the first element. It's the first element, yes, and it's the second element. For each fiber, there is an element which switches components of these fibers, but for each element of this group, one can contain some components of singular fibers. So there is no cyclic abstractions in this case.
What happens with, say, the lower left component? Take the left fiber, take the upper component of the fiber.
Yes.
And apply, say, the first element and then the second element.
Yes. It goes to this component. There is the third. No?
Yeah.
Yes.
It will just be an action of different
Yes.
formulas.
Yes. So, considering any one of 3 elements non-trivial in C2 squared, I can go to the rational surface in my NLP. But if I consider the whole group, which is not cyclic, then the cohomologies for these groups are not trivial, and so it is not statically rational anyway. Well, but actually, the good idea that cyclic subtraction is necessary conditions for cases 1 and 3. So there are not only static rational surfaces, but surfaces without cyclic abstraction in the grades of degree 1, 3, and 4, and for the grades of degree 2, there are not 4 but 7 possibilities of groups which don't have cyclic abstractions.
So can you repeat the previous thing? So for D1 and 3, the
Right,
cycle
there's
are
D1 or 3, if the surface is minimum, then there is cyclic abstraction. For D equals to 2, if x is minimum, then there is cyclic abstraction in all cases, except these 4 and 3 more. But for these 3 more cases, one have subgroup isomorphic of this one, and so there is other abstraction. Well, now using the Smith, we want to prove something. Let's try to do it.
So in particular, in this three additional cases, you have a structure of conic bundle, or
I have a structure of the group which is conjugate to this.
the conic bundle with respect to a smaller group.
Yes, I have abstraction that in my group G there is a group, non-abelian group of order 4, non-cyclic group of order 4, which is conjugate to this group in while group E8 or E7, etc.
And you said that this group also provides an abstraction. So
Yes, provide an abstraction but not cyclic.
so you can compute the homology with respect to.
I don't do this. This was done for Kudowski's, Probability, and Spassman. I don't compute yes.
For fibers there. So.
You see that there are only one conic bundle which is have all non-trivial echelons, and this conic bundle is the only known example. I wrote down it. It's with fibers for points of degree 1 and 3, and all the other conic bundles with 4 singular fibers, they are all non-stable correlation. Well. Now let's start the proof. What our method? What do we have? We want to find possibilities of G such that there are no cyclic abstraction. We start from X, and the one the lattice is Z. What do we have? We found first step. If there is any subgroup H in X and H in G, such that the variant Picard number on the direction of H is 1, then we can replace X, G by H. So you see, if we find cyclic abstraction is in smaller group, then this abstraction is in the biggest group. The next step. Assume that there is a normal subgroup. It can be trivial normal subgroup. And G is by the assumption invariant Picard number under the direction of n is greater than 1. So what do we do? If we have the invariant Picard number under the direction of n is greater than 1, then we have n equivalent minimal model program. It will be our key idea.
But possibly with conic bundle, right?
Yes, it's no problem. So the first step of proof, which I don't want to prove, it's classify conic bundles without cyclic abstraction. It's theory of group, just no geometry in this case. Well, moreover, we can replace the group n by stabilizer group of invariant Picard lattice of n. This group will be normal in G2, and also the invariant Picard number for the new group will be the same. Well, after replacing, we have the following. Since now N is coincide with its stabilizer group, we have that the group G by N faithfully acts.
What do you mean by stabilizer? You mean the stabilizer of the sublattice or the pointwise stabilizer of the sublattice?
Hmm?
So,
Peak pointwise.
No, sublattice.
so you allow non-trivial action on this peak x bar n.
So stabilizer X or doesn't X?
Well, I say that there are no elements which do not lie in N, which acting on this lattice non-trivial.
Yeah.
Not trivially. That any element which is not in N acts on this lattice, or acts on this lattice.
It may not act
Not
on
trivial.
at all.
I mean, question, every element of G preserves this sublattice obviously, because N is normal. So.
Yes, N is
So
normal. Yes.
But they means.
So it's the kernel of the actual, it's not
Yeah, yeah.
stabilizer, it's the kernel of the actual.
Yeah,
Yes, it's the stabilizer of 1 point.
Of every point. It's
Pointwise.
pointwise.
Okay.
Yes, the kernel of the actual.
Kernel section, yes. Well, the group, now the group G by N factor is faithfully acts on our invariant lattice. Well, now, the next step, if there is intermediate subgroup is H normal subgroup in G by N, then we have the following sequence. N, then H tilde, and then H tilde is normal in G. Yes? Or something like this, yes? Since, yes, we consider pre-image under the quotient map and have this possibility. Now for this triple we can consider invariant Picard number under the action of H and then do the following. If it's equals to 1, we will replace the pair Gn by the pair H1, H tilde n, and if this number is greater than 1, we replace the pair Gn by the pair G H tilde. So, and what do we do now? What idea of all this process? Now we have the following setting. That X depends the surface, it is G minimum. There is a subgroup normal in G such that X is not minimal under the action of G, and moreover, the quotient G by N is simple, there are normal subgroups. Cycle of prime order on an abelian. Yes, this is the simple and G by N acts on this lattice. Well, now we can start to prove something. First I want to say a few words about an abelian case. this is quite technical, and the idea of proof, I don't want to write it down, is that for this situation we can find an intermediate group, H in a simple group. So you see G by N is simple group. We find H in this subgroup, not normal, but just a subgroup such that invariant binomial is also equal to 1. For example, if we have representation of group A5, then for cases which we consider Picard numbers equals for representation set of whole group A5 or for just representation of elements of order 5 in this group. So something like this. And consider this case, it's simple. So we can assume that G by N is a group of prime order for cubic surfaces. For cubic surfaces, it's C2, C3, or C5. Since the order of wild group can be divided for any other prime number. Well, let's start doing these cases. Yes, Japan is CP. We consider the action of G on orthogonal completion on this vector space. How does it can be written down? The normal subgroup N acts like something this, where this coordinate corresponds to basis for this subspace. Yes, and any element G which lies in G but not lies in N acts in the following way. It has a number of roots of order root of pth degree from 1. It can be diagonalized, yes? So we choose a basis here such that the element in G by N is diagonalized. So all those elements are just have their common part. We don't act here, and they can be some action, and there is some numbers of collections of pi minus 1 roots. So it's not necessarily one group of pi minus 1 roots of its degrees, but this some number of this. Well, I will just wrote down it by example. And also what we do, we say that G has the order Pn just by raising it to some powers coprime to P. Well, let's start consider examples. How does this work? For example, first case is that G by N is C5. And then we have cubic surfaces from this moment. So actually all these methods work for all the plate surfaces of degree 2 and degree 1, also degree 4. But for lack of time, we just consider cubic surfaces. First case is C5. In this case, one have G the following. Right? It acts on invariant and invariant lattice by multiplying of all fourth roots. So the order eigenvalues of C5 should be there should be roots from the 5 or more degree from unite, and also they should be form so the action of mg is defined over q, yes, over z. Before we pass to orthogonal part, it's defined over z, so its all eigenvalues should be 1, and they form a groups of conjugates. So you see that for an element of order p, the group of conjugates of 1, its eigenvalue consists of p minus 1 values. So if one has one group for element of order 5, there are not other groups of order 5, and what I mean to say that it acts trivially on those vectors, which are non-trivial, where n is non-trivial. So what does we have in this situation? We have that g is equals to c5 by n. Since you see the element g acts only here, the subgroup n acts only here, and we just reformulate our stations. Well, and the order of n is something like 2k to 3n's, since it can be an element of order 5 in this group before there are only 2 eigenvalues for any element of n non-trivial, so there are 2 or 3. And what do? We find, we just consider a normal subgroup in n, yes, and then we replace our pair Gn by the pair H tilde, which is C5 times n. It's normal in C5 times n, which is the group G. We replace our pair Ng by the pair H tilde G. Repeat this procedure and come to this case, but not for the group C5, but for the group C2 or C3. That's like this. Not of index divided by 5. Yes, the next case is elements of order 3. That's what can we say about if p is equal to 3? Then there are following results which comes from tables. That all elements of order 9 are best for any n. I write here n, since it can be not only for field surfaces but for all surfaces. And there are 3 adjuncts classes of elements of order 3 in WE6. They denote by their Carter's graph, and it's A2, A2 square, and A2 cubed. So what's the difference between, if we consider eigenvalues of the action of this space, of this element, then here we have one pair of conjugate eigenvalues, and on the other ones, here we have 2 pairs of conjugate eigenvalues. Yes, omega is the third group of unite. Here. And here we have 3 pairs of conjugates. Whereas, as one can easily see, the invariance of the action of this element of this space, the only invariant is just 0. Therefore, for this action, for action of one element, the cubic surface should be minimal, and if cubic surface is minimal, then the element is better. Since k squared is 3 for cubic surface, so it's better element. These 2 elements are good. Well, Now we should consider two cases for element for the quotient of order 3. The first case is when the invariant Picard number, this invariant Picard number is 5. What does this mean? So it can be greater than 5, since otherwise we have that n has type a2 cubed. So here we have that gx on our space in the following way. Moreover, G, we assume that there is cyclic abstraction in our group. So if there aren't any cyclic abstraction, then G can't have type A2 in Q. So there's just two unities here. Yes, and actually in this case one have that G is C3 times N. Yes. Moreover, we can assume that N has order 2 in the kth power, since otherwise we can consider an element of order 3 here. Obviously there aren't any element of orders 5 or greater prime numbers. So if there is an element of order 3 and M, we just can multiply this element by our element G and get an element of type A2 in Q. So that's impossible. Then it's two group, and moreover I can see that this group can contain only elements of order 2, since elements of other order don't commute with element of type A2 squared. And thus is a Abelian group. It has representation, and that means that there must be elements which act as multiplication by 2 minus 1s. Here and here. Therefore, if we consider product of these two elements, we have element of the following form of order 6. And from tables of conjugacy class, one can see that this elements is not, there isn't an element in the Weyl group of WE6 which has this number of eigenvalues. And even if there was such an element, it would be bad, since you see here is 6 non-trivial eigenvalues. Therefore, for these elements, invariant Picard number should be equal to 1, and so it's minimal cubic surface, and it should be bad. Yes, this the first case. And the second case is when the invariant Picard number under the action of n is 3. Well, what in this case we have? We have that element as in the following way, and in this case we can write down, as in two previous cases, that G is a derivative product of cyclic group of prime order and N. Since the element G can have type A2 or as A2 squared. That's both situations are possible. In the first situation it's a derivative product, but in the second situation it's not so. So what do we have? We have lemma. The following lemma is about order of n. If order of n is equals to 3n, but n is not divided by 3, then G can be chosen as of type A2 or type A2 in the cube. So either we have a red element in this situation, or we have our group as a David product. How to prove this lemma? Well, consider the group N. By Salov's theorem, there is 3k plus 1 subgroups in N, which are conjugate to each other and conjugate to isomorphic to subgroup of order 3. Therefore, the action of G by conjugation on N stabilizes one of these groups. That means the generator of this group, H, is invariant under the conjugation of order G. And H has order 3. And then we have the following 3 possibilities. It's possibility first that, well, G is something like this. These two values for invariant elements of N. Well, the first possibility, if the H has type A2 squared, but then one can multiply G by H or H squared and get an element of type A2 in the cube. So in this situation we have a bad element, so it's not good for us. And the second two possibilities is that H is of type A2. So there are two cases. One that the, oh yes, these two elements can use so they can be simultaneously diagonalized. So the first situation, the non-trivial eigenvalues have this actually the same eigenvectors, and we can multiply G by H or H squared and get an element of type A2. In the second situation, we have that they have different non-trivial eigenvectors, and just one multiplied to another, we have an element of type A2 in the third form. Well, how to use it for our aims? Let's start at MMP. First, we assume that there is an invariant line on our cubic surface A. Well, let E be an invariant line, one line. Then, the pickup group of into nth is generated by E, GE, and G squared E. Yes? Since one can check that these three classes, they give lattice of rank 3. Yes, moreover, since one has invariant pickup number after the action of whole G equals to 1, we have that this sum must be proportional. One can show that actually it is equal to anti-canonical class. What does this mean? When we have this equation, it means that G has type A2 squared or A2 in the third power. So why is this so? Because since the element of this type of A2, it don't has triangles of lines. So we put each line into a line which is coincide with this line or don't intersect this line. These three lines are intersecting each other. Well, if we are in this case, there we are done. And if we, in this case, we can should prove something. Oh well, what should we prove? These are three lines, yes? But also for each of those three lines, we can consider the following construction. If there is a line on cubic surface, then one can consider set of planes passing through these lines. These planes are parameterized by P1, and each of these planes intersects our cubic surface in line E and a conic, which can be non-smooth in 5 cases. That means that the linear system minus kx minus E gives a conic bundle structure. Well, that's very good. So we have some exceptional curves and invariant, and we have an invariant conic bundle structure. So we can write down how the minimal model problems looks like. So at first we can contract a curve, one curve, for example, GE contraction. One can easily check that the class of this line and class of fiber of these conic bundles, they intersect at 0, so it's component of exceptional component of the degenerate fiber of these conic bundles. And then we have conic bundles. Moreover, since we have invariant Picard number equals to 3, this end of minimal model problems. This conic bundle is minimal. For minimal conic bundles, we don't know maybe, but I calculated all groups that don't have cyclic obstruction. And more, we can assume that there aren't elements of order 3 in this group, since the order of this group acting on the base of degree 4 can be divided by 9. So actually there are 5 possibilities of two groups, and for each of case of this possibility, one can consider the action of G by N by conjugation, find an element which is fixed by conjugation. That element will commute with N, but just from the structure of these groups, element of such types in W6 can commute with element of type A2 squared. So we have contradiction in this situation by some calculation. And what about other possibilities? If there is no invariant lines, if there are no invariant lines and no invariant conic bundle structure, since if there is an invariant conic bundle structure, then there is, just by this formula, a 2 section of this conic bundles, which is line on cubic surfaces. Then one can easily check that the minimal model problems can be made only in 2 ways. So equivariant contraction of 2 lines and then 3 lines and getting a minimal the best surface of degree 8 with rho equals to 1, or 2 equivariant constructions of triples of lines. Well, in this case, we have that the group N is a subgroup in S3 times S3, and moreover, it should, the image of N under pressure of the each of factors should contain a group C3. Therefore, an element of type something like, well, there is an element of order 3 in N, which acts non-trivially on the both of these factors, and this element should have type A2 squared. And when we look here onto G and those elements, we say that under multiplication by H or by H squared, yes, also one characteristic that it's invariant conjugation by G, so these two elements commute, sometimes diagonalize it, and by multiplication of these two elements with some power, so that one can get a better element of type A2 in the group. And in these situations, one can find other type of bad elements, just see that the N should be subgroup in the following group. So this C2 corresponds to equivalent blow up down. This pair of points, this S3 to this triple of points or lines, and C2 is just a group which switches components of the P1 cross P1, which is the vector surface of degree 8 over algebraic closure of field. And find for this situation the better element 2. So, I think there. Yes, I don't need many time. I think, yes, I just say a few words about case C2 and we end at this moment. So, for the group of order 2, we have the following idea, that C2 acts as -1 on our space, which is orthogonal to Kx. Yes? It just multiplies an element of this space by -1. This is linear action, and under the action of C2, the only invariant vector should be 0. Well, we can write down the section in terms of Morricone. So, what do we have? It's Morricone. Here is something like here. It's Morricone of for minimal for N and P. Here there is a class of minus Kx. So that there is any extreme array E, extreme array of N and P. How to find the image of E under the action of G? Yes, G is, as usual, an element lying in G, but not in N. So it's element of order 2. We can assume that it has order 2 or 2 in some powers, but in the more recurrent text an involution. We just consider a plane passing through the rays corresponding to minus Kx and E, and the image of G of E should be second derivative in the plane spanned by E and minus Kx. But there are some problems with this. Let's try to do this method for cubic surface. Actually, it's very simple for the best surface of degree 2 or the best surface of degree 1, since the corresponding external array is just the image of the first external array under the action of Geyser or Bertini evolution. And for cubic surface, this doesn't work in this world. So, if we have E an exceptional curve is aligned, then, as we saw in the previous situation, one has that minus Kx minus E is fiber of conic bundle. So these two external arrays the second external ray which lies in the plane passing through E and Kx, has other type. So it's impossible for n in this setting to be aligned or to have an invariant line. This action is impossible in terms of the action. If E is a pair of